All right, let's dive right into this explainer. Today, we're going to demystify the complex, invisible world of the atom, and we're going to do it using some pretty brilliant architectural metaphors. It's actually wild to think that absolutely everything around us, the air we breathe, the coffee in your mug, even the screen you're looking at right now, is made of atoms. But because they are so impossibly tiny, trying to grasp how they actually work, well, it can feel a bit like trying to solve a puzzle in the dark. So today, we're turning the lights on. We're going to break down the structure of the atom in a way that's organized, visual, and just totally intuitive.
It's such a fundamental question, right? And to answer it without getting totally bogged down in academic jargon, we're going to build a mental blueprint, literally, from the ground up. Scientists debated this exact question for decades, pitching all sorts of crazy models. But to truly understand chemistry, physics, and really just the nature of reality itself, you need a solid picture of what's happening inside these microscopic building blocks. By the end of this explainer, you're going to have a crystal clear map of the atomic world.
So, here is our roadmap for today. First, the basic building blocks. Second, energy, light, and elevators. Third, orbits versus orbitals. Fourth, the atomic blueprint. And finally, seeding the electrons.
Okay, Section 1, the basic building blocks, the foundation of all matter. Before we can even touch quantum mechanics or energy shells, we've got to know the players on the field. Every single atom operates as a tiny self-contained system, and the absolute key here is this holy trinity of particles. You've got your heavy protons and neutrons locked safely right in the center, and the incredibly light electrons just buzzing around in the empty space outside. Protons carry a positive charge, think P for plus. Neutrons are completely neutral, so zero charge there. Together, they make up the nucleus, that heavy, dense core of the system. On the flip side, the electrons, which carry a negative charge, they don't hang out in the nucleus at all. They exist in the vast, seemingly empty space surrounding it. And in a perfectly neutral atom, the number of positive protons perfectly balances out the number of negative electrons.
Moving right along to Section 2, energy, light, and elevators. How atoms glow.
Ever wonder why certain elements give off distinct colors, like that intense, bright yellow light of sodium vapor you see in some streetlights? To understand the atom, we actually have to understand light, because light is exactly how atoms communicate what's going on inside to the outside world. Every atom has a special light fingerprint. This happens because light behaves like a wave, and the specific color we see depends entirely on its wavelength and frequency. Imagine you're watching waves roll onto a beach. The distance from the top of one wave to the top of the next, that's the wavelength. How often those waves crash over your feet, that's the frequency. In physics, these two are linked by a super simple formula. The speed of light equals frequency times wavelength. Basically, it's a giant seesaw. If the frequency goes up, the wavelength must go down. Really close together waves have a much shorter wavelength. And those specific wavelengths? They correspond to specific colors of light.
Now, think of Niels Bohr's model of the atom like an elevator. An electron absorbs a jolt of energy, maybe from heat or electricity, and uses it to ride the elevator up to a higher floor, which we call an excited state. But here's the thing, it can't stay up there forever. When it inevitably drops back down to its comfortable, lowest energy home, its ground state, it has to get rid of that extra energy. So it spits it out as a photon of light. Because different elements have totally distinct distances between their elevator floors, they release different specific wavelengths, which gives each element its own unique color signature.
Which brings us to Section 3, orbits versus orbitals, the quantum shift.
To truly map this out, we actually need to upgrade Bohr's idea and make a major conceptual leap, because as it turns out, we cannot accurately know an electron's exact position and its velocity at the very same time. So we have to trade those predictable fixed roads, the orbits, for the probability clouds of modern orbitals. This is a massive shift in how we view reality. Bohr thought electrons orbited the nucleus on a definite path, literally just like the Earth going around the Sun. But in the modern quantum mechanical model, things get fuzzy. Electrons move so incredibly fast and act so bizarrely that tracking their exact route is physically impossible. Instead of a clear road, we're left with a blurry map of probabilities. And this brilliantly illustrates the whole foundation of the quantum mechanical model. We can only say where an electron is likely to be. We absolutely cannot track its exact route. I actually want you to completely banish that image of a tiny solar system from your mind. Instead, picture an orbital as a thick cloud. Where the cloud is thickest, you have a really high chance of finding an electron. Where it's thin, the chances drop. It's basically the difference between knowing exactly what highway a car is speeding down versus just knowing a person is probably somewhere inside a specific neighborhood.
All right, Section 4, the atomic blueprint, mapping the atom's internal structure. With that whole quantum shift out of the way, we can fully deploy a fantastic metaphor to map out the atom's internal structure. Yes, electrons live in probability clouds, but those clouds aren't just chaotic and random. They are highly organized into very distinct levels and shapes. We can frame the atom perfectly as a building. The main energy shells, those are the floors. The subshells, those are the rooms. And the orbitals are the individual seats where the electrons sit. Keep this analogy in your back pocket and atomic structure becomes incredibly simple. The atom is the house. Inside the house are main floors, called shells. On each floor are rooms, called subshells. Inside those rooms are specific chairs, the orbitals. And who sits in the chairs? The electrons, of course. Let's actually look at how this building is constructed.
If you want to figure out the absolute maximum number of electrons that can cram onto one of those main floors or shells, you simply plug the shell level, n, into this elegant little formula. 2n squared. That letter n just stands for the principal energy level. So, you want to know how many electrons can live on the very first floor? Well, n equals 1. For the second floor, n equals 2, and so on. Higher shell numbers generally just mean they're farther away from the nucleus and pack more energy.
Let's see how this plays out. As we travel from the ground floor, which scientists call the K shell, up to the M shell, the capacity for electrons jumps exponentially. So, for the K shell, n is 1. Using our formula, 2 times 1 squared is exactly 2 electrons. The K shell is a tiny floor. Now the L shell, n is 2. 2 squared is 4, times 2 is 8 electrons. The M shell, where n is 3, holds up to 18 electrons. And if you kept going up to the N shell, where n is 4, it holds a whopping 32 electrons. Literally, the higher up the building you go, the wider it gets.
Now step inside those floors and we find our subshell rooms, named S, P, D, and F. Each one contains a specific number of orbital seats that max out at exactly 2 electrons each. This is where the architecture gets really detailed. The S room is cozy. It only has 1 orbital seat, so it holds 2 electrons total. The P room is bigger, with 3 seats, holding up to 6 electrons. The D room has 5 seats for 10 electrons. And that massive F room? It has 7 seats, packing in up to 14 electrons. Just remember the golden rule here. It doesn't matter what type of room it is, a single orbital seat can never hold more than 2 electrons.
To pin down the exact state of any electron in this giant house, scientists use 4 quantum numbers. Basically, they tell you the floor, the room's shape, the room's direction, and the spin of the electron in its seat. Think of these 4 numbers as an electron's VIP concert ticket. The first number, n, tells you the floor. The second, L, tells you the shape of the room, whether it's an S, P, D, or F room. The third, ML, tells you exactly which way that room is pointing in 3D space. And finally, MS tells you the electron's spin. Because you can have 2 electrons jammed into one seat, they have to spin in opposite directions so they don't repel each other too much. One spins up, one spins down.
And that takes us to our final section, Section 5, seating the electrons, the house rules.
Atoms don't just throw electrons in at random. They are incredibly efficient and follow strict protocols to keep energy as low as possible. It is exactly like filling a movie theater. You grab the cheaper, lower energy seats first. You only allow 2 people per seat, and everyone sits single before they start pairing up with strangers. Let's break those laws down. First, the Aufbau principle. This just means you start at the ground floor. You completely fill the lowest energy levels before you even think about moving up. Then, the Pauli exclusion principle, which we just talked about. An orbital seat holds a maximum of 2 electrons with opposite spins. And Hund's rule? That's just pure human nature. If you walk into a row of empty seats on a bus, you don't sit right next to someone if there's an empty seat available, right? Electrons do the exact same thing. If a room has multiple equal energy seats, like a P room with 3 seats, 1 electron goes into each seat first. They only start pairing up once every single seat has at least 1 occupant.
So when we write out the electronic configuration for real elements, the main number is the floor, the letter is the room, and that small superscript tells us exactly how many electrons are sitting in it. Let's look at hydrogen. Its atomic number is 1, meaning it has 1 electron. That single electron goes to floor 1, room S, giving us 1s1. Helium has 2 electrons. They both fit nicely into the S room on the first floor, giving us 1s2. Now check out carbon, with 6 electrons.
The first two go to the 1S room. Bam, that floor is full. The next two ride up to the second floor S room, making it 2S2. We've got 2 electrons left, so they move into the next available room on the second floor, the P room, giving us 2P2. It is just a logical, step-by-step process of filling the available seats from the ground up.
We have successfully mapped out the atom's architecture today, from the dense central nucleus all the way out to those vast probability clouds of electrons, all governed by these strict quantum rules. If you can explain the difference between an orbit and an orbital right now, you've officially unlocked the atomic blueprint. But I want to leave you with one final thought to chew on. If atoms are mostly empty space, and you are made entirely of atoms, why don't you fall right through the chair you're sitting on? Well, that is the bizarre reality of quantum repulsion. The negative electron clouds in your body are pushing against the negative electron clouds in your chair. Nothing ever truly touches. So next time you knock on wood, just ask yourself, what else about our solid reality is just a brilliant, invisible illusion of energy? Keep questioning, and we'll see you next time.